let's talk about how to find a potential function of a given vector field, thereby showing that the vector field is conservative. First of all, we need to be mindful that it's not every given vector field that has a potential function. And in fact, there are many vector fields out there that do not have a potential function. And therefore, we should not attempt to find the potential function until we are certain that the potential function exists. And because in this question, it's asking us to find the potential function, so we can assume that the potential function exists, and then we proceed from there, which means that we are able to treat the first, second, and the third component of the vector field as partial x, partial y, and partial z of a function f. Okay, so let's go over the process of finding this potential function. We're gonna start by setting potential function f(x,y,z) equal to the antiderivative for the first component with respect to x, which is partial f partial x dx. And then we're gonna plus a function that is expressed purely in terms of y and z. The reason why we do this is because there's some information inside the potential function that we might have lost in the process of partial differentiation with respect to x. You can imagine if there's something that is purely expressed in terms of y and z, then that thing will go to 0 if we take partial x on both sides. And that thing cannot be restored in the process of only integrating it with respect to x. And therefore, we need to assume that this is going to be the part that we might have lost, and then the steps of finding the potential function is equivalent to not only finding this one, but also finding the function in terms of purely y and z. Okay, so let's try to find this one. Right, integrating this with respect to x, this one is going to be this. If we integrate this with respect to x, it's going to take us to x squared y. So we can replace now this one by x squared y. Next step, we're going to take partial y on both sides of the equation to make use of the rest of the information that is given. Okay, so we're going to take partial y on both sides, then partial y is going to give us x squared, and then this one's going to become partial g, partial y. Okay. Because we have known what the partial f partial y is, which is already given here, and we also know this one, so we can solve for partial g, partial y from this equation. It's going to be this guy minus this guy, which is x squared plus 2y z cubed minus x squared. So we can have x squared cancel, leaving us with only 2y z cubed. So we write it on the side. Okay, so this partial g, partial y can be solved. That is this minus that. It's going to be 2y z cubed. Okay, this one. And next, we will do the same for the variable y to try to solve for partial g, partial z. Okay, so we take partial z on both sides of this equation again. And left hand side is going to become this. And then for the right hand side, this part does not contain variable z, so it's going to go to 0. And then this one's going to go to partial g, partial z. Okay, we can see from this equation that partial g, partial z is exactly partial f, partial z, right? But we have been given what the partial f, partial z is, which is this one. So we're going to write it on the side. Partial g, partial z is going to be partial f, partial z, which is 3y squared z squared plus 2z. Okay. Now we can erase these two equations to save us some space. And the next step is that we're going to find this function, this function g of y and z by making use of information here. Okay, we're gonna set up the same thing, which is similar to the first equation here, by setting that this g function is gonna be the antiderivative with respect to the first component, right, for this expression. So that's gonna be partial g partial y dy. And then, because there's some information inside this function that we might have lost in the process of partial differentiation with respect to y. So we need to assume that this is a function that is purely in terms of z, just similar as the first step here. And then finding this function is equivalent to not only finding this part, but also finding this part. Okay, so because we know partial g partial y is this one, so if we integrate this with respect to y, it's going to take us to y squared z cubed. So we can replace this by y squared z cubed by taking the antiderivative. And then we will look for this one. Okay, we look for this by taking partial z on both sides of this equation. Okay, partial z, and then partial z for this one is gonna take us to 3y squared z squared, and then partial z for this one is just purely dz dh dz. Okay, again, from this equation here, we can solve for dh dz, because that is partial g partial z minus this one. But we know what the partial g partial z is. Partial g partial z is this guy, right? This guy minus this guy. So we're gonna have the first term cancel with this term here, leaving us with dh dz equal to 2z. Okay, dh dz equal to 2z. And because of that, we can find the function h by integrating this with respect to z. So we see that h of z is z squared plus c. And we know that c is just any constant, and then we usually take z, the constant c equal to 0, because for convenience, right? We're not asked to find all the potential function. We are asked to find just a potential function, so we can just take c equal to 0. Okay, so after we have this function h, we will replace this with z squared. So we now have this function g, and then we're going to substitute this with that in the expression here. So we will have the entire potential function, which is plus y squared z cubed plus z squared, which is the potential function that we have been looking for. The last step is to, just to be safe, we should check that this is indeed the potential function that we are looking for. We check that by taking the partial x, partial y, partial z, respectively. We check that it gives us the first and second and the third component, so that we can make sure that our calculation is correct.